Welcome to Care Coordination and Interoperable Health IT Systems, Standards for Interoperable Health IT, Lecture C. This unit will cover the following learning objectives. 1. Explain why standards are required, how they are developed, and how adoption is encouraged. 2. Name and describe the types of interoperability standards available. 3. Summarize functionality of HL7 V2, CDA, CCDA, and FHIR. And 4. Recognize HL7 V2 messages, CDA documents, and FHIR resources. This lecture will focus on the functionality and messages of HL7. HL7 version 2 was originally created in the 1980s as a standard to communicate healthcare information between systems and hospitals. As of 2016, HL7 has already published HL7 version 2.8 and is working on version 2.9. HL7 version 2 has achieved widespread global adoption as a general healthcare interoperability standard, both within and between varieties of organizations. HL7 version 2 defines standard message layouts and the rules on how they are exchanged. The most common message types implemented within an organization using HL7 version 2 are ADT messages, which are also referred to as admit discharge transfer messages. Other common message types are order messages, result messages, clinical reports messages, or medical records messages, charges, scheduling, medication administration, and medication dispensing. The most common uses of HL7 version 2 between organizations are messages for public health communications, such as reportable results, syndromic surveillance, and immunizations. Another common use is for order and result communication between doctors and commercial labs. A third common use of HL7 messages is for identifying and matching patients in a health information exchange. HL7 version 2 is also a common vehicle providers use to share health information about patient visits to a health information exchange. Imagine a typical HL7 version 2 messaging scenario where a patient is admitted to the hospital. In HL7 version 2 terms, this event is referred to as a trigger event. The trigger event then leads to the patient admission being recorded in the registration system, and a message is generated and sent to the receiving systems. The message will be sent to the hospital EHR and the hospital laboratory. It might also be sent to the hospital pharmacy, the public health authority for syndromic surveillance purposes, or a health information exchange. The health information exchange might then notify the patient's primary doctor that the patient has been admitted to the hospital. Each system that receives the admission message would process it based on their application logic. In many cases, a new visit record would be created on the receiving system. A real-world event happens, such as the admission of a patient. We call that a trigger event. This event is recorded on the sending system. The sending system then creates a message based on the HL7 standard and sends it to the receiving system. For example, the admission might be recorded on the patient registration system, and then the message notifying about the admission would be sent to the laboratory information system. The receiving system receives the message and either fully processes it or at least saves it to a recoverable resource. If it can receive the message successfully, it sends back a positive acknowledgement message. Otherwise, it sends back a negative acknowledgement message. This example message is communicating information about the hospital admission of Adam Everyman. It consists of header information about the message, followed by information about the trigger event, followed by information about the patient, followed by information about the patient's visit at the hospital. MSH, EVN, PID, and PV1 are all known as segments. Let's look more closely at the message and its segments. Each message is made up of segments. A segment is a group of related fields, Each segment begins with a 3-segment identifier and ends with a carriage return. The very first segment of every message is the message header segment, whose segment ID is MSH. The ordering of segments in a message matters and are defined in the HL7 message definition for that message type. Let's look at an example message definition. Each type of HL7 V2 message is defined in the standard with a message definition. The message definition shows what segments can appear in a message, how often, and in what order. It gives the segment IDs, short descriptions, and provides the chapter in the HL7 version 2 specification where the segment is defined so that the reader can go and get additional information. If a segment is optional, it is surrounded with square brackets. If the segment can repeat, it is surrounded with curly braces. The message definition shown here is for a patient admission message. It requires the MSH, EVN, PID, and PV1 segment. All the other segments are optional. The SFT, ARV, ROL, and NK1 segments can repeat. For example, a patient admission can have 0 to any number of next of kin or associated parties because the NK1 segment is optional and repeats. In our example message, the trigger event was patient admission. All trigger events are represented by 3-character codes. The trigger event for patient admission is AO1. Examples of other trigger event codes include AO2 for patient transfer and AO3 for patient discharge. In the example message, there are 4 segments: MSH, EVN, PID, and PV1. Note that there were none of the optional segments that were specified in the message definition. The first segment is MSH, which is the message header. The MSH segment tells the receiver about the message itself, the time and date it was created, the trigger event, the message type, and what version of HL7 was used. The second segment is the event segment, or EVN, which says more about the trigger event and when the actual event happened. The third segment is the patient identification segment, or PID, which gives the patient's demographics. The fourth segment is the patient visit segment, or PV1, which gives information about the patient's hospital visit, such as the location of admission, the attending doctor, and the admitting service. Each segment has a segment definition. This is the segment definition for the patient identification segment of PID. A segment definition includes a sequence number, which is just a logical sequence of the field within the segment, a suggested maximum length for the field, and a data type for the field. The data type can be simple or complex, and if it is complex, then it is further broken up into components and subcomponents. Special characters are used to encode or decode HL7 messages. The segment terminator ends every segment and cannot be changed. The field separator separates adjacent fields. The repetition separator separates repetitions of a field, and the component separator separates components of the field, and the subcomponent separator separates subcomponents of a component. HL7 has special encoding rules which the sender follows to encode a message in the HL7 V2 message format for transmission. The sending system follows the format of the message definition as it creates the message. For each segment, it follows the order of fields in the corresponding segment definition. The sending system puts each field component, subcomponent, and repetition in order based on the segment definition. If it finds that a field, component, subcomponent, or repetition is not present, it skips it and continues with the next field component, subcomponent, and repetition. So then that would mean that if there is not present for a particular field, you get it with 2 vertical bars next to each other and nothing in between. However, if the field component, subcomponent, and repetition has the null value, meaning that it is an empty field on the sending system or it is deleted, the sending system would put double quotes to show that it has been deleted or it is null. For example, if the birth date is empty on the sending system, The sending system would put double quotes in between the vertical bars. If there are no more fields, components, subcomponents, or repetitions required and no data left to send, then separators are not required at the end and a carriage return is added to end the segment. Let's look at encoding a PID segment. In this case, we have a patient named John J. Jones with the medical record number 123456. That medical record number was assigned by the assigning authority, Good Clinic. If you look at the PID segment, you will figure out that PID 5 is the field that would contain patient name, and PID 3 is the field that would contain the patient identifier. To build the segment, first you would put the segment ID, which is PID. Then you would proceed to the first field with the vertical bar, and since you have no value for field 1 or field 2, which are set ID and external patient ID respectively, you would just put more vertical bars. You do have values for field 3, which is internal patient ID, and is broken up into components. The first component is the medical record number. Then you do not have anything for the 3.2 and 3.3 components. However, you have the assigning authority value, which is Good Clinic. Moving on to field 4, which is alternate ID, you do not have any value, so you put nothing. For field 5, which is patient's name, you put the last name in 5.1 component, then first name in 5.2 component, and the middle name or initial in 5.3 component. If any of those fields had nulls because it was deleted or nothing existed, then you would see double quotes. Note that we ended the segment after the fifth field, or PID-5, because there is no more data, and it is that last required field in the segment definition. The segment can send right after the name field, since the sender has no more PID information about the patient to communicate, and no fields after field 5 are required in the segment definition. In summary, an HL7 message is made up of segments. A segment is a group of related fields. Each segment begins with a 3-character segment that ends with a carriage return. The very first segment of every message is the MSH segment. The fields in a segment can sometimes be further broken down into components and subcomponents. Field components and subcomponents are stringed together in a linear fashion with delimiters, such as a vertical bar, tilde, circumflex, and ampersand. These delimiters separate the fields of the components, subcomponents, or repetitions, which is for the message header. We have been looking at a patient administration message. So now let's look at a laboratory message as an example. This particular picture is from an implementation guide and shows how the lab results flow might work. Implementation guides constrain standards and give more information. The picture demonstrates a use case and the constraints within this specification. One constraint is that it is only for laboratory messages. Another constraint is that it requires that all lab tests be encoded using the LOINC standard terminology. In this particular scenario, the doctor sends an order to the lab results interface. The lab result interface sends the order to the downstream system, which is in this case the lab. The lab receives the order and specimen, sends preliminary results, and sends final results later. The provider could provide corrections to the result. So there is actually a bidirectional workflow that is happening here. Now that we discussed the workflow of a laboratory message, let's look at the structure of the laboratory results message. This HL7 V2.4 message definition has been abbreviated for teaching purposes. Like the patient administration message, the results message also has a required message header segment, or MSH. The PID and OBR segments are also required. The OBR, Observations Report segment, contains fields related to the execution of the lab order by the lab. For example, it contains the time the test was resulted. The actual test result is recorded using one or more OBX or observation segments. For example, an electrolytes test would have several observations represented as OBX segments. It would have one for every electrolyte, such as one for potassium and one for sodium. Let's look closer at a sample results message. You will see the MSH segment, the PID segment, the OBR segment tells us the test is a glucose reading, and the OBX segment, which contains the value of the result. Here are the fields for the OBX, the observation details segment. The common fields include identifier, units, references range, abnormal flags, responsible observer, and observation method. HL7 version 2 has limitations. There are too many options and ambiguity in the specifications. It is too generic, intended to work with a wide variety of use cases, instead of being fully constrained to work for specific use cases. It's not well integrated with terminology standards. There are gaps in functionality as well as overlaps with the functionality of other standards. Conformance is not often well specified. As a result, to make two systems interoperable, when both use HL7 version 2, requires site-specific analysis, specification, and coding. When implementing HL7 version 2, the implementer will ideally implement an HL7 V2 implementation guide or profile, which gives detailed guidance and constraints and would reduce implementation variance and cost. Speaking of implementation guides, here are some HL7 version 2 implementation guides that are required for ONC 2014 and 2015 certifications for public health. The examples here are for immunization messaging, syndromic surveillance, and laboratory reporting. This concludes Lecture C of Standards for Interoperable Health IT. To summarize, Health Level 7, or HL7 version 2, is a widely adopted general healthcare interoperability standard. HL7 version 2 defines standard trigger events and message types and defines how the messages are exchanged. Two common message types are the patient admission message and the laboratory result message. A HL7 message is comprised of strings of fields grouped into segments and separated by encoding characters. Although HL7 version 2 is widely adopted, there is a lot of variances between implementations. To help resolve this, implementation guides are encouraged.